Today our topic is electron gain enthalpy. What is electron gain enthalpy? When we add an electron to an atom, a neutral atom, and that is in the gaseous state, sometimes energy will be released or energy may be absorbed. So there is an enthalpy change during the addition of an electron to an atom, a neutral gaseous atom. That enthalpy change is known as electron gain enthalpy. The enthalpy change accompanying the process of addition of an electron to a neutral gaseous atom to convert it into negative ion is defined as the electron gain enthalpy. As I told you, when an electron is added to an atom, sometimes energy may be released or sometimes energy may be absorbed. Because after absorbing this electron, the atom is changing to a negative ion as indicated here. X plus E minus gives X minus, a negative ion. When we consider elements such as halogens, it needs only one more electron to get noble gas configuration. That means to go to a highly stable state. When it is going to a highly stable state, its energy will decrease and therefore it will release energy. So that is a negative electron gain enthalpy. Here you can see, in the case of group 17 elements, it has very high negative electron gain enthalpy because they can attain stable noble gas electronic configurations by picking up an electron. They are going to more stable state. If they are going to more stable state, their energy will decrease. When its energy decreases, it will release that excess energy in the form of heat energy. On the other hand, noble gases have large positive electron gain enthalpy. Why? Noble gases have a stable configuration. They are highly stable. If you add one electron to noble gas, that will go to an unstable state, means high energy state. If you want to change it from a stable state to high energy state, surely you have to supply energy. If the system is getting energy, if the system has a gain, we will indicate it with a positive. So it has a positive electron gain enthalpy. Now we can see the electron gain enthalpy values of a few elements. Group 16 and group 17 are given. You see the values. This group 16 and group 17 elements have negative electron gain enthalpy values. Negative electron gain enthalpy values. And these negative values, it is decreasing as we move down the group from sulfur to polonium in group 16 and from chlorine to astatine in group 17. But the value of oxygen, that is minus 141, less than that of sulfur. As we move down the group, the value is decreasing, but in the case of first element, the value is less than that of the next. For oxygen, minus 141, for sulfur, minus 200. For fluorine, minus 328, for chlorine, minus 349. So even though it is decreasing down the group, we can identify two anomalous behavior here. Anomalous behavior of oxygen and anomalous behavior of fluorine. Okay, we can see the reason for this anomalous behavior later. Now the variation of electron gain enthalpy left to right in a period. Electron gain enthalpy, that is depending on the atomic size. As the atomic size decreases, the attraction from the nucleus will increase. As the attraction increases, the addition of electron to the atom, that will become more easy. So we can say as we move from left to right in a period, the electron gain enthalpy, negative value of electron gain enthalpy increases. As we move from left to right in a period, the negative value of electron gain enthalpy increases. What are the reasons? Decrease in atomic size, increase in effective nuclear charge, strength of attraction increases. Electronic configuration is other reason. For fluorine, it requires only one more electron to get noble gas configuration, so it is ready to accept electron. But in the case of lithium, it has only one electron in its outermost orbital, and if it can't remove that electron, it will get a noble gas configuration. So lithium has no tendency to accept electrons. Always it is ready to give electrons. So electronic configuration is another factor. Now down the group, what is the variation? The negative electron gain enthalpy decreases down the group. As we move down the group, electrons are moving more and more away from the nucleus because of the increase in number of shells or because of increase in size of the atom. Therefore, it is difficult to add an electron to the atom, or they are not ready to accept electron. As a result, what is happening? The negative value of electron gain enthalpy decreases down the group. Again, what are the reasons? Increase in atomic radii, decrease in effective nuclear charge. As the radii increases, the distance between nucleus and outermost electron increases. Therefore, effective nuclear charge decreases, screening effect of inner electrons. Inner electrons are hiding the nuclear charge. These are the reasons. Now, the anomalous behavior, anomalous changes. Already we mentioned that is in the case of oxygen and fluorine. Oxygen has lower electron gain enthalpy than sulfur. Fluorine has lower electron gain enthalpy than chlorine. In these two cases, the reason is the same. In case of oxygen, the electron filling is taking place in second orbit. 2s2 2p4. In the case of fluorine, electron filling is taking place in the second orbit. 2s2 2p5. But in the case of sulfur and chlorine, it is happening in third orbit. 3s2 3p4 for sulfur and 3s2 3p5 for chlorine. In the case of second orbit, that orbit is very small. Already it has, in the case of fluorine, already it has 7 electrons in that small orbit. If it is accommodating one more, surely the electron-electron repulsion will increase. That is ready to accept electron, but there is a problem of space to accommodate. So we can explain the reason for anomalous behavior of fluorine and oxygen as when an electron is added to oxygen or fluorine, the added quantum level is n is equal to 2. That is a smaller level and suffers significant repulsion. There is large repulsion between the electrons. But in the case of chlorine and sulfur, the quantum level is n is equal to 3, third quantum level. The added electron occupies a large region of space and the electron-electron repulsion is much less. That is the reason. So if you are writing answer in a single sentence, what you have to write? The electron-electron repulsion is more in oxygen or greater in oxygen than that in chlorine. That is the reason. Similarly, the electron-electron repulsion in oxygen is greater than that in sulfur because of the small size of oxygen. You can write the answer in a single sentence. Okay, I think it is clear to you. Now here you can see a question. Which of the following will have the most negative electron gain enthalpy and which the least negative? And you have to explain your answer. Here, which are the elements given? Phosphorus, sulfur, chlorine, fluorine. As we move from left to right in a period, negative value of electron gain enthalpy increases. So this element, first three elements belong to third period. All the three are in third period. So from left to right, that means phosphorus to chlorine, electron gain enthalpy increases, negative value. So out of these three, chlorine has higher electron gain enthalpy. But fluorine, that is above chlorine in the group, but it has an anomalous behavior. Its electron gain enthalpy is less than that of chlorine. So the element which has the most negative electron gain enthalpy is chlorine. I explained the reason also. It is having the least. Surely it is phosphorus because it is the first element in that particular group, and fluorine is an exceptional case. Surely fluorine has higher electron gain, negative value of electron gain enthalpy than phosphorus. Okay. Now electronegativity. It is the ability of an atom to attract bonded pair of electrons towards itself. In the case of chemical bond, two atoms bonded through chemical bonds. And that atoms may attract electron pairs towards itself because it is giving an electron. If the bond is formed by sharing of electron, it may try to take its electron back. Or it may try to get the other electron also. So all the atoms have such a tendency to attract these electrons towards itself. And electronegativity is a qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself. That is called electronegativity. It is not possible to measure the exact value of this ability. There is no instrument to measure the exact value of this ability. Then what is possible? Only comparison. If fluorine has this much of electronegativity, then what is the tendency of chlorine? Or what will be the value of chlorine? Only such a comparison is possible. So based on this, many scales developed to measure the electronegativity or to express the electronegativity. Examples: Pauling scale, Wilkin-Jaffe scale, Alder-Roscher scale. These are some of the scales. But widely accepted one is Pauling scale. And in our periodic table, and in your class table, the electronegativity values are given in Pauling scale. And in Pauling scale, the highest value is 4. And that value is given to fluorine. But that value is assigned arbitrarily. Then, when you compare it with the fluorine, we can give some values to other elements. So the most electronegative element is fluorine, and in Pauling scale, the electronegativity value of fluorine is 4. Then if you come to chlorine, its electronegativity is less than that of fluorine. So the value will be less than 4. Electronegativity, if it is the tendency to attract electron, then there is another term, electropositivity, that is the tendency to give electron. Electropositivity is there. Metals are highly electropositive. Or we can say fluorine is the least electropositive element. Fluorine is the greatest electronegative element, or most electronegative element. At the same time, it is the least electropositive element. So alkali metals are highly electropositive. They have large tendency to give electron, highly electropositive. Electronegativity variations left to right in a period, electronegativity increases. Left to right in a period, electronegativity increases. That we already mentioned. Alkali metals are electropositive, halogens are electronegative. So we can say electronegativity increases from left to right in a periodic table. What are the reasons? We cannot find out any other reasons. The same reasons that we explained in the previous cases. Decrease in atomic radii, increase in effective nuclear charge, electronic configuration. These are the reasons. And down the group, electronegativity decreases. What are the reasons for that? Increase in atomic radii, decrease in effective nuclear charge, screening effect of inner electrons. Screening effect or shielding effect of inner electron. Periodic trends in chemical properties. Now we explain the atomic properties. We can see periodic trends in atomic properties. Similarly, in the case of chemical properties, there is periodic trend, and the chemical properties are depending on valence shell electrons. And the number of valence shell electrons will explain the combining capacity of each element. So that electrons, the valence shell electrons are very important, and that valence shell electrons determine the chemical property of each element. Based on these valence shell electrons, we developed a term known as valence or valency, which explains the ability of an atom to combine with other elements. And the valency is defined as number of electrons in the outermost shell, or 8 minus number of electrons in the outermost shell. Here we can see the table. In the case of first group, number of valence electron, 1. What is the valence? 1. Group 2, number of electrons, valence electrons, 2. Valency, 2. Group 13, number of valence electron, 3. Valency, 3. Group 40, number of valence electron, 4. Valency, 4. Group 15, number of valence electrons, 5. It requires 3 more electrons to get noble gas configuration. So it shows the valency 3 and 5. 8 minus 5 and 5. 3 and 5. Group 16 require only 2 more electrons. So it has valency 2 and 6. Group 17, 7 electrons. Only 1 more electron is needed. So it has valency 1 or 7. Group 17 can donate all the 7 electrons to more electronegative atoms. For example, IF7, a compound between iodine and fluorine. Iodine will give all the 7 electrons to fluorine. So in that compound, the valency of iodine is 7, but fluorine is -1. And in group 18, you know, they are not ready to accept electron or release electron. It has completely filled configuration, stable configuration. So 8 minus 8, its valence is 0. But now a number of compounds of noble gases are identified, and therefore they are in that compounds they are showing valency up to 8. Using periodic table, a question using periodic table, predict the formula of compounds which might be formed by the following pairs of elements, silicon and bromine. What is the valency of silicon? Silicon belongs to group 14, valency is 4. And bromine belongs to group 17, valency is 1. It can be 1 or 7, but silicon is more electropositive, therefore bromine has valency 1. Now write elements in the order of their electronegativity. Less electronegative first, then more electronegative. So silicon first, then bromine, SiBr. Interchange their valencies. So give the valency of bromine to silicon, Si, 1. Give the valency of silicon to bromine, Br, 4. SiBr, 4. 1 only to represent it. So SiBr4 is the formula of the first compound. Aluminium and sulfur. Aluminium group 13, valency 3. Sulfur group 16, valency 2. So Al2S3. Al2S3. That's the formula of the compound. Anomalous properties of second period elements. All the elements of second period are the first elements of each group, except noble gases. All the elements of second period are the first element of each group, and this first element is shows some difference from other elements in the group, especially difference in their properties. What are the reasons for this anomalous property of the second period elements or the first element of each group? There are a lot of differences, and what are the reasons for that? If you analyze all the elements in the second period, you can identify they are very small in size as compared to other elements of the group. They have high electronegativity. Similarly, high ionization enthalpy, absence of d orbitals. In the second period, which is the orbital, second orbital has only 2s and 2p levels, 2s, 2p. Second orbit, 2s and 2p orbitals are present. There is no 3d orbital. But in the third period, 3s, 3p, 3d orbitals are present. So in this case, they have no d orbital. These are the reasons for their anomalous behavior. Now, diagonal relationship. If we examine the periodic table, we can identify a particular similarity in properties of first element of a group with the second element of the next group. And the periodic table, it will be present diagonally, therefore we will give the name diagonal relationship. And if we examine the periodic table as a whole, we can identify 3 such pairs, diagonal pairs having similar properties. The diagonal pairs are lithium and magnesium, they are present diagonally. Lithium is the first element of the first group, and magnesium is the second element of second group. Beryllium and aluminium. Beryllium first element of second group, aluminium second element of 13th group. Boron and silicon. Boron first element of 13th group, silicon second element of 14th group. It is known as diagonal relationship. What is the reason for this diagonal relationship? Because they have almost the same size, almost the same ionization enthalpy, almost same electronegativity. Then charge to radius ratio also equal. Charge to radius ratio also equal. Because of these things, they are showing diagonal relationship. Now the last point, periodic trends in chemical reactivity. Not only in chemical properties, but also in chemical reactivity, there is periodic trend. In short, I will say the elements in the extreme left of the periodic table, that is alkali metals, they are highly reactive. Similarly, elements in the extreme right of the periodic table, halogens. Halogens are also highly reactive. Noble gases are not reactive because they have completely filled configuration, except noble gases. If we consider that side, halogens are highly reactive. And as we move from group 1 to the middle of the periodic table, the reactivity decreases. Similarly, as we move from group 17 to middle of the periodic table, the reactivity decreases. Or as we move from left to right from the middle of the periodic table, the reactivity increases. We can see this periodicity in the formula of the compounds also. For example, when we consider the oxide, sodium combines with the oxygen to form Na2O, magnesium combines with oxygen to form MgO, aluminum combines with oxygen to form L2O3, carbon combines with oxygen to form CO2 or CO. Two possibilities are there. Nitrogen can combine with oxygen to form many compounds. NO, N2O, NO2, N2O4, N2O5. Such many compounds are formed. Sulfur, SO2, SO3, chlorine. Chlorine forms many oxides up to Cl2O7. Okay. If we compare the properties of these compounds, there also we can see an interesting variation in its property. The oxides of alkali metals are highly basic, but the oxides of halogens are highly acidic. So what we can say, the basic strength of oxides decreases from left to right in a period. But the acid strength of oxides of elements increases from left to right in a period. For halogens, the oxides are acidic. But for alkali metals, the oxides are basic. So all of you write down the notes and complete the assignment, submit it in time. A few questions are given here, write the correct answers of it. Okay, we can stop it here.